In the third video, we are looking at some of the reliability model used to analyze reliability data. It has to be said that Weibull++ contains a wide range of models used for reliability engineering, 6 of which are Weibull related, but there are also log normal model, exponential model, gamma model, log logistic model, which are also particularly for the log normal, widely used in reliability engineering. So the first model we are looking at, this data set, it comprises of 16 data points, so 16 failures, and we are looking at 2-parameter Weibull. It's a 2-parameter Weibull model, and it generates the 2-parameter in the analysis. We have the beta, which is the shape parameter, and depending on the value, it gives us an indication whether we are in infant mortality for beta less than 1, or random failure for beta around 1, and for wear out for beta greater than 1. Like in this case, we are on a very gentle wear out. And the eta, or the second parameter, or characteristic life, gives us an indication of how long will the product last. And eta is linked to the probability of failure, and it corresponds to a 63.21% probability of failure. So by just looking at the parameter, we are able to have an indication, without even looking at the chart, having an indication of the behavior of our product in terms of whether we are into a wear out, or whether you're into infant mortality and what type of wear out, and at what number of hours we're getting about 63% probability of failure. So that is a very informative model. Another strength of the Weibull model is the fact that with very small data set, I'm able to construct quite an accurate analysis. I don't want to be bogged down with the exact number, but I can, with a sort of handful of data points, I can certainly produce some projection, some valid projection. And then obviously it depends on the accuracy of the data being collected. And the other thing is also the graph itself is very informative. Here we have an indication of the graph on the Weibull paper. And based on how the points align the model, which is the blue line, we are able to, first of all, establish whether the model is valid or not, but also we are able to establish whether there are some behavior that could be linked to different types of failure mode interacting, or whether there is a batch problem, that kind of problems. So that makes a statistical method much more practical in its use. The second model we're looking at is used to analyze, like in this case, is a very different type of data set. This data set comprises of 1 failure and 12 suspension. So clearly is a data set with a high level of uncertainty. And the model we have selected is 1-parameter Weibull. We could have selected an exponential model to analyze these data, and in fact that would have been fine. The only difference is with an exponential model, we are assuming an exponential behavior. With a 1-parameter model, we have the option of suggesting a shape parameter based, say, on historical data, based on engineering judgment, what we consider to be the behavior of this data set. This could be, for example, a new version of a product. So this is very useful in situation where we have a very preliminary data. So we have simply 1 data set, 1 point, and we can suggest a behavior based on previous knowledge, and that's particularly useful. The third model we're going to look at is looking at a very different data set. In this case, we have a data set that comprises both failure and suspension, but it also comprises of different failure modes. So we collected information about how the product failed, and we want to make a good use of that information. And so what we're using here, we're using a competing failure mode, or CFM model, that enables us to analyze both the mechanical failures and the seals failure. And then the resulting that is the 2 data set, the mechanicals and the seal, but also the resulting model. The resulting model is the product of these 2 data set. So it does not generate a final Weibull model, but it generates a resulting curve. And this is very useful in situation where, as we said, we've collected our data, but together with the number, we've also collected specific information on how the product failed. And based on that, we can decide perhaps to provide some solution to a particularly critical failure mode based on the graphical output. So these are three of the models we sort of included in Weibull++. In the next video, we'll be looking at how we can refine our projection. Thank you for watching. See you in part 4.